Hello and welcome to day 6 of our probability notes. Today we're going to talk about the OR rule and mix in some probabilities about and some conditionals. So I'm going to bring it back to our tree diagram from last lesson where you're making a sandwich. So remember, you had 2 choices of bread, white or wheat, and then you had to select a meat and you had 3 choices, turkey, ham, or roast beef. So here's your choice of bread, and then from there, your choice of meat. And as we discussed in our last lesson, this shows that we have 6 possible options to pick 6 possible options of sandwiches. Referring to the tree diagram from yesterday, what's the probability of selecting a sandwich with wheat bread or turkey as a meat? So if I look at my diagram, I see with wheat bread, there are 1, 2, 3 out of the possible 6 options that satisfy wheat bread. As far as turkey goes, there are 2 options. Now, obviously, there was an overlap here where this guy fell under both category. Now that's the same sandwich, right? So we don't want to count them twice. So that means we have 1, 2, 3, 4 possible sandwich options out of 6. So for 6 or 2/3 would be our probability. Now this relates to the OR rule that I've actually been teaching you throughout the way, where the OR rule says you can do the probability of wheat plus the probability of turkey, and then subtract the overlap because you don't want to count it twice. So for probability of wheat, you had a 1/2 chance, or I'll actually write it like this, 3 out of 6 chance of picking a sandwich with wheat bread. For turkey, as I said, there were 2 options for turkey, but there was 1 option that was both wheat and turkey, so it fell into both categories and we only want to count it once. So if we do this, this would be 3 plus 2, which is 5, minus 1, which is 4, which is 4, 6, which checks exactly what I came up with in the tree diagram. So this formula right here allows me to solve for OR problems without having to draw a tree diagram. All right, so a recent survey of 833 students at Amherst High School found that 453 students participated in sports, 52 students participated in band, and 21 students participated in both sports and band. Find the probability that a selected student participates in both sports or band. Okay, so look at what they gave you. You know there's a total of 833 students in our survey here at Amherst High School. The probability of selecting somebody in sports was 453 out of those 833. Probability of being in band was 52 out of the 833. The last thing they gave you was the people that are in both sports and band. So probability of sports and band. There's 21 of those students, again, out of the total of 833. So right now, all I've done is just listed out what was given to me. Now, if they want me to solve for the OR, then I'm going to have to use my formula. So probability of sports or band is equal to sports plus probability of band minus the overlap, so sports and band, and now I just plug in what I know. Okay, so again, this is my probability of sports coming right there. This is my probability of being in band. And then remember, these 21 people are in both, and we don't want to count them twice, so I subtract it once. Add those numerators together, keep the denominator the same, and you should get 484. So the probability of selecting someone in sports or band is 484 out of 833. And that's how you would use your OR formula to solve. Now in the past, we probably would have drawn up a a two-way table and tried to use the numbers there to help us. But like I said, I've been teaching you this a little bit along the way, so hopefully this doesn't seem too crazy new to you. So of the 453 students that participate in sports, 18 are on the softball team and 22 are on the baseball team. If you were to construct a Venn diagram of the situation, what would it look like? So if you have, of your 453 students on softball and baseball, you got to ask yourself, can those circles overlap? Since we will have females on the softball team and males on the baseball team, in theory we shouldn't have either of them overlap. So this would be my softball team. This would be my baseball team. This would be a Venn diagram where they do not overlap. This is an example of something called mutually exclusive. This just means that these two events cannot occur at the same time. So if I go back to my example with Amherst High School, are the events mutually exclusive, aka is it possible for us to select a student that's both in bands and sports? And yeah, it's possible for them to be in both. So therefore, they are not mutually exclusive. So mutually exclusive means they cannot occur at the same time, and since you could be in band and sports, those events were not mutually exclusive. All right, moving on to example 3 on the next page. Josie will soon be taking the exams in math and Spanish. She estimates that the probability she passes the math exam is 0.9, and the probability she passes the Spanish exam is 0.8. She's also willing to assume the results of the two exams are independent of each other. So that just means that whether she passes math or not has no influence on whether she passes Spanish. We want to calculate the probability she passes math and Spanish. So we know probability of passing the math exam is 0.9. Probability of passing the Spanish exam is 0.8. Based on what we discussed last lesson, we know for and probabilities, we will just multiply them together. So all I'm doing is taking the 0.9, multiplying him by the 0.8, and getting 0.72. And that's the probability of math and Spanish. So I'll just add this here as well. Find the probability she passes at least one of the exams, aka what's the probability she passes math or passes Spanish? So based on our OR formula, we know this is the probability of math plus the probability of Spanish minus the probability of math and Spanish. It's just a formula. I know the probability of math is 0.9, probability of Spanish is 0.8, and then math and Spanish, remember we just found, is 0.72. So take a moment, type that in your calculator. And you should end up with 0.98. So there's a 98% chance that she would pass math or Spanish. All right, so let's move on to dice problems. So I'm sure most of us know that a die is a cube where each side represents a number 1 through 6. Let's calculate the probability of getting an even number followed by a number below 3 in 2 rolls of a fair die. So you have to understand that in reading this, you have 2 separate rolls, and each roll is independent of each other. This is an AND probability because you're having 2 rolls independent of each other. You're getting an even number and then getting a number below 3. So let's think about each scenario separately. Let's think about the numbers you have. So 1, 2, 3, 4, 5, 6, and the probability of getting an even number. Well, you know your options for even numbers are 2, 4, and 6, which would be a 3 out of 6 or 1/2 probability. Now let's look at the next one. 1, 2, 3, 4, 5, 6. in your next roll, you're going to get a number below 3. So that would be 1 and 2. So that is a 2 out of 6 probability. So since each roll is independent of another, this is just an and probability, all we're going to do is multiply these probabilities together. So 3 out of 6 times 2 out of 6 would be 6 out of 36. And you can reduce that or not, it doesn't matter. As long as it's mathematically equivalent, 6 out of 36 would be your probability. Okay, calculate the probability of rolling a single die and getting a 2 or an odd number in a single roll. So notice the difference. In example 4, we had 2 separate rolls, each independent of the other. In this one, we're rolling the die once and asking for an or probability. It's not like you get one thing and then the other. It's, okay, in one roll, these are the things I want. All right, so list out your options. 1, 2, 3, 4, 5, 6. Probability of rolling a die and getting a 2. Okay, that would be that guy. Or, I'll change pen colors, getting an odd number. So odd numbers would be 1, 3, and 5. Look at how many total things that I circled. 1, 2, 3, 4. That means the probability is 4/6. Now, if you were to use the OR rule, that would be the probability of a 2, which was 1 out of 6, plus the probability of an odd number, which was 3 out of 6, and there was no overlap, so therefore you'd end up with the same thing as me as 4/6. But I like to just map it out. Calculate the probability of rolling a die and getting a 2 or a multiple of 3. So again, another OR probability in a single roll. 1, 2, 3, 4, 5, 6. Probability you roll a 2 is 1/6. And then a multiple of 3 would be 3. Oh, wait, hold on a second. Let me change my color. 3 and 6. So that's coming from the second guy. How many total things did I circle? I circled 3, so the probability would be 3/6. All right, example 7, calculate the probability of getting an odd number followed by a number above 3 in 2 rolls of a fair-sided die. Okay, so again, this sounds a lot like what I did up here, where this was an and probability. These two were ors because they were in a single roll. So now I'm back to an and probability. So let's think about each separately. Probability getting an odd number, 1, 2, 3, 4, 5, 6. My odd numbers are 1, 3, and 5, so that's 3 out of 6. And then probability of getting a number above 3, that would be 4, 5, and 6. Okay, that means in order to get the and here, we're just going to multiply 3/6 by 3/6, and that would be 9/36. And that's your probability. Now, I recognize that some of you guys probably don't need to map this out. You can probably just think in your head, oh, probability of odd would be half of that, so 3/6. Probability of greater than 3 would be 3 options, 3 out of 6. Like, I recognize that a lot of you will probably be able to figure these out in your head, which is fine. I just need to see this work. Okay? So I'm just explaining for those that might need a second to see where I'm getting the probabilities from. All right, last example on this page. Calculate the probability of rolling a die and getting a prime number or an even number in a single roll. Now, prime numbers are numbers whose multiples or factors, are only 1 in themselves. So, for prime numbers, 1, 2, 3, 4, 5, 6. So by definition, it's a number greater than 1 whose factors are only 1 in itself. So for instance, 2 is a prime number because its only factors are 1 and 2. 3 is prime because its only factors are 1 and 3. 4 is not prime because I can come up with 4 by doing 1 times 4 and 2 times 2. So he's not prime. But 5 is, and 6 is not because 6 is 1 times 6 and 2 times 3. Now again, by definition, 1 is just not a prime number. That's just how we decide. Now the next condition here is to have an even number. So on the same diagram here, even numbers would be 2, 4, and 6. So you'll see I had some overlap here at number 2, but you're only going to count them once. How many total numbers did I circle? 5, so that means the probability is 5 out of 6. Now again, if you wanted to use the OR formula for this, the prime numbers were the red circles, so 1, 2, 3, so that was 3 out of 6 for prime. The even numbers were 2, 4, and 6, so 3 out of 6. And then remember there was an overlap, so that was 1 out of 6, and that's how we end up with 5/6 as well. So just another way to do it. All right, lastly, we're going to talk about card problems again in order to do some probabilities and mix in some ands and ors and stuff. All right, so calculate the probability of drawing one playing card from a deck of 52 cards and getting an ace or a red. So first of all, an ace is, or are those guys, there's 4 of them, so that's 4 out of 52. How many cards are red? Well, that would be half of the deck here. So keep in mind if there's 52 cards, 26 of them are red. But then you can't forget that some of the aces were also red. These guys right here, right? And we don't want to count them twice. So that means I'm going to subtract 2 out of 52 because there were 2 aces that are also red. Denominator would be 52. This would be 30 minus 2, which is 28, and that would be your probability, 28 out of 52. All right, I'm going to clear this off so I can use it again. Calculate the probability of drawing one playing card from a deck of 52 and getting a king or a heart. Okay, so again, there are 4 kings in a deck. Hearts represent a suit, which is 1/4 of our deck, which keep in mind each suit is 13, so that would be 13 out of 52. Okay, now I gotta double check. Are there any kings that are also hearts? This guy right here. That's a king who is also a heart, and I can't count him twice. So I'm gonna subtract the 1 out of 52, and that would give me 16 out of 52. Calculate the probability of drawing one card from a deck of 52 and getting a club or a 6. Okay, so clubs are these guys at the top, and there's 13 of them because that's 1/4 of our deck. 6s, there's 4 of them. Now, are there any clubs that are also 6s? Yep, right there. That's where they overlap, and I cannot count him twice. So I'm going to subtract the 1 out of 52, and this one will also be 16 out of 52. Calculate the probability of drawing 2 cards from a deck without replacement and first getting a king and then getting a queen. So notice how the terminology changed. In the other problems, I was picking 1 playing card, just like how I was doing 1 roll with my die problems. Now I'm going back to picking 2 separate cards. As we discussed in our last lesson, without replacement means you don't put the card back. So now we're back to doing an and, where the rest of these were or probabilities. All right, so what is the probability of getting a king? Well, I know there are 4 kings in the deck out of 52. Now, if you don't put the card back, that means there's 51 cards left to pick from. How many of them are queens? 4. Multiply together, top would give you 16, and bottom would give you 2, 6, 5, 2. All right, we have one more problem to do, and it just ties together our OR formula. So in a recent survey of West Seneca West High School 11th grade students, it was found that 56% were female, 58% liked math as their favorite subject. Additionally, 76% of all students are either female or liked math as their favorite subject. What percent of 11th graders were females and liked math as their favorite subject? And justify your answer, which just means show your work. So I'm going to list out what they gave me. Probability of being female was 56%. probability of liking math was 58%. And then they said the probability of being female or liking math. So math or female. I'll just do F for female, was 76%. They want me to solve for the and. So because they gave me an or here, that's giving me a hint to then just use my or formula. So I'm going to write out my or formula. So probability of math or female equals probability of math plus probability of female minus, and I'll just do the little and symbol for the both where they overlap. Let's plug in what I know. Math or female, they told me, was 76%. Math was 58%, and female was 56%. I'm going to call the and that I'm solving for X. So if I grab my calculator, 58 plus 56 is 114. So then if I do 76 minus the 114, that'll give me negative 38. Now keep in mind that equals negative x. You want to solve for x. So we divide by negative 1, and that means x, which is our and, is a positive 38%, and that's your answer. So sometimes students will think with a question like number 12, where they're solving for the and here, that they just multiply them together like how they did for the deck of cards up here. But you can't multiply them together because you don't know enough information about their independence. So again, all you have to do is realize that if they're giving you the or here, they want you to use that for the or formula, and then you just plug in and solve for your missing value. And that is introducing you guys to your or formula, where it applies, and how it compares to the and that we did on Friday's lesson, or our last lesson. So hopefully this helps. If you need to rewatch this video will be posted on Google Classroom, so you can always revisit it.